Good evening, everyone. Today we are starting to talk about wave functions, which is the fundamental topic for quantum mechanisms, quantum mechanics, and Schrödinger's equation. Today we are going to start with one-dimension Schrödinger equation with independent of time, which is independent of time. So let me introduce myself. You can call my nickname Arian. I know this is weird spelling. Yeah, yeah. And I'm 17 years old, so which means I'm year 12, and I'm interested in chemistry and physics, so I'm trying to start a YouTube channel to explain some question and topics related with organic chemistry, inorganic chemistry, physical chemistry, and somehow somehow I came with the idea why not start with quantum mechanics, because quantum mechanics is very important in late 20th century's discovery, and this is now widely used in explaining some anomalies in chemistry, and also used to also the frontline theories are used to calculate some values such as the wavelength of a substance absorbed in atmosphere, or the rate of reaction somehow. Okay, now let's really begin with my new YouTube channel. See, I'm a little bit rusty in my English, so my apology, my fault. Okay, you see the title, Wavefunction. You see it's big. This seems to be frightening and shocking and crazy, right? But to be honest, it's a fraud. It's fraudulence. So you don't have to be panic for quantum mechanics. It's basically as easy as your A-level physics program. It's just based on some mathematic deductions and mathematics relationship like calculus, like partial differentiation and operators. So today is just an introductory part, an introductory topic, and I hope it's easy. Yeah, I hope it's easy. So the subtitle is the Schrödinger, no, capital S, Schrödinger equation. We probably know about Schrödinger's cat, right? The cat is dying and alive simultaneously. That's weird. That's how quantum mechanics works. You know, people are not talking about quantum mechanics like some alien species. They think it's weird, right? Yeah, I do the same. Most people. I think quantum mechanics for human are weird. But before 17th century, when Sir Isaac Newton has published his theory, his Newton's first law, which is the statement that when there is no resultant force applied, a substance or a mass continues to be stationary or travels in constant direction and constant velocity. Before this, people think that the force is the reason why substance and objects are keep moving instead of the reason of alternating the situations, the the conditions of those objects are moving. So you see, I'm a little bit rusty. I'm really rusty, to be honest. Yeah. And first, I will write the Schrödinger equation here. To be honest, it is to be to be frank, this is a pretty long and complicated differential equation, and it is a second-order differential equation, which I will never understand as a mathematician. But anyway, we can find some approaches to solve it and simplify it. Yeah. So this seems to be complicated. But anyway, we will take a closer look at this. First, I have to say V is potential energy. Potential energy. And this huge stuff, this huge guy, is the kinetic energy. Which is more important. You see, the main character here is this Greek symbol. This Greek symbol is C. This symbol represents all the dynamical information about the particle, about the helpless particle, such as its momentum, which is this, and direction. No, and oh my god, and the position it is. Yeah. So this is quite informative and useful when we are talking about a particle, especially some particle with microscopic scales such as muons, electrons, and sometimes protons or alpha particles. But alpha particles is quite macroscopic compared to electrons. Anyway, we'll start this. And E is the total energy. This is pretty reasonable due to the law of conservation of energy, isn't it? In all the physics spaces, in all the isolated spaces, total energy always equals to potential energy plus kinetic energy. That's common sense, right? So, but anyway, although this makes sense, if some guy like me just stand on street and telling people walking by about my new discovery, about a new subject called quantum mechanics, they'll think this guy is crazy. He's a psychopath, isn't it? So we have to prove it. We have to validate the possibility of this Schrödinger's equation. First, I will expect everyone watching this will know that there's a guy called de Broglie, and he said this. This is de Broglie's wavelength of a particle. This is Planck's constant wavelength, lambda. Okay, this is Planck's constant, which approximately equals to this value, 6.626 times 10 of the power of minus 34, and this is momentum, of course. We don't have to say any more about that. So we begin with the left-hand side of Schrödinger's function, Schrödinger's equation. Like this. First you will say, oh, I know this. I really know this. This is equal to this, because we are assuming V, the potential energy, equals to 0. Since we cannot use any valid approach to normalize this potential energy, and we're assuming it's 0. As further study goes, we will see that there is a model called particle in a box. Like this. This is 0, this is L, and in the shaded parts, V equals to infinite, and here in this middle part, V equals to 0. Here is the assumption we are taking, and Yeah, that's the assumption we are taking. And as you know, most of the particles are moving in simple harmonic motion. So also we just assume it to be like this. And also in further lecturing, we will discuss about this function, and we will find that it is actually essential and unskippable when we are discussing with wave functions and quantum mechanism, especially in further stuff. Anyway, let's get started. So we have to get the second derivation, I hate this word, the deviation of C. And you know, for anyone who have take A-level math and who is able to pass, we are able to know a function like this. Yeah, it is easy, right? This is the first derivation, and then we can know like this. Here is minus, take here, take here. Be vigilant at this, because if you don't, this will be a horrible mistake. And as we know this, the left hand side will be equals to this. See why I'm writing wave function instead of this sine function? Because this is exactly Cx. Okay, now I have to add a point. You see this weird looking thing? This is called h bar, which is Planck's constant over 2 pi. Yeah. So if we know this, we can say that this is basically, we can rearrange this formula to something like this. Oh, I'm sorry, I made a mistake. Here, you see, here, it's lambda, and I wrote L here. I don't know what's wrong with me now, but I'll fix it. Let's see, I'm fixed. So here. And things are simple now. We can cancel this, cancel this. Basically, that's it. We can say h squared over 2m lambda squared cx, left hand side. Okay, as we get this, how do we prove the possibility of Schrödinger's function? That's easy. Since the Broglie wave said that momentum of a particle equals to Planck's constant over its wavelength, so we know that p squared equals to h squared over lambda squared, which is this part of the function. So we know left hand side equals to p squared over 2m cx. And you know what? This is best part. Yeah, I would say this is best part. As we know, p equals to mv squared 2 over 2m. And we can still cancel this, and we find it is actually kinetic energy of this particle times c. And since we assume that the potential energy is zero, so kinetic energy equals to the total energy, which means this equals to total energy times Cx. Left hand side left hand side always equals to right hand side, and proved. That seems to be easy, right? It's just basically some mathematics rearrangement and some drudgery about sines, cosines, differentiation, and drinking Monster drink like me. Yeah, okay. Let's turn to the next part. And you see we're talking about x. And so this is called the one dimension, 1D, time independent, which means the energy of this system doesn't change as time goes. Time independent wave function. Now it's actually the rudimentary part of our first topic. Yep. And what can we do with this Cx? What can we do about it? What can we do? That's a good question. So we are turning to 1.2. This is the second part. And we introduce you something called the Born interpretation. Interpretation. The Born interpretation says for a particle with wave function c at x, the possibility. Remember, possibility is not the same as possibility. Yeah, that's English class, isn't it? Of finding the particle between x and x times dx, or x times delta x, it doesn't matter, is proportional to cx modulus squared dx. Yeah, and then we will see how this works, how this pretty thing works. We also assume the particle is trapped. Oh, we need a straight line. It is trapped in one-dimensional space, like this, right? Like this. This is wave function. This is x. And if we want to evaluate the possibility for the particle to be here, to be inside of this poor little thing here, and this is x plus dx. So we will see that this is equals to p equals to dx. That's basically pretty simple and pretty logical. It's easy to memorize. And you know, the total possibility of any events in this world is just 100%, isn't it? There is 100% that some guy got lottery top prize tomorrow. There is 100% of this particle in this room. So we will say that this equals to 1, because the total possibility of the particle to appear at all of x values equals to 1, which means the possibility for this particle to present is 1. That's pretty easy. I hope it goes well. And in some cases, in the C expression, there is something like this. This is just complex numbers, and I squared equals to -1. So we can rearrange this to C times conjugate C. When there is no I, there is no complex part. We just say it's C squared. Anyway, we can use this. We can use this above. And this is the probability density. Probability density of our wave function. And this is called probability amplitude of our wave function. Then probably you'll ask what will happen if we have a three-dimensional space, such as in real life, in real world. Okay, we will say that this, which is simplified to this expression below. This is the Greek letter tau, yeah, equals to 1. So that's basically something about Bohr interpretation. interpretation. That's something pretty simple, I would say. And if we really have a particle, we really have a real life wave function, we'll find that sometimes the wave function is 0. So the point that the wave function is 0 is called a node. It's called a node. This is where we cannot find the particle. There is zero possibility for us to find that particle, because since Tx equals to 0, T squared x must be equals to 0, which means there is zero possibility for us to find it. And we'll turn to the mathematics part. This is 1.3 normalization. I would say when I was walking through this part like 2 days ago, this is the most challenging part. But to be honest, it is not challenging at all, since it's just A-level mathematics and basically logic. So yeah, well, I hope I can explain it well, since it's my first time to start a YouTube channel. Let's get started. So some of you may have noticed that in this function we have seen every term, right? We have seen every term. Yeah, this is pretty noticeable, because if we have t in every term in this polynomial, we can say that one of the most significant property of Schrödinger's equation is that when the both side of it is multiplied by n, where n is a constant, the equation is still valid. It still gives same solution as when there is no n. And n is called normalization constant. Normalization constant. This is widely used in our calculations in quantum mechanics, because for every function we get it from solutions of Schrödinger equation, and Schrödinger equation is this second order differentiation equation, which means we'll get two unknowns, and it is pretty difficult for us to evaluate A and B, which are the two unknowns. So we use normalization to help us. Okay. For example, a very good example will be this. We have a particle, which Cx equals to sine pi x m. So we have to normalize this. Until now, you maybe have no idea how can I handle with this crap. Yeah, because nobody can deviate it from my poor explanation. So let's get started. If we multiply n with t, which gives the same solutions for the equation, we can know that if we if we do this, just recall that it is the formula to calculate the density, the probability density for a particle to present in a region. Yeah, we can do something like this. We can see that this is equal, right? This is equal. And since they are constant, we can get this. Yep. Yep. And in this function, I think I forgot a very important statement in this question. This question is this particle, the particle is trapped between x greater or equal to L and smaller or equal to L, greater or equal to 0. So we can know this. We can know this, right? It equals to 1 because according to Born's interpretation, this has to be 1. This has to be 1. This is just the probability for this particle to present. It is of course 1. And we can now solve this very basic integral, which gives us the this is square. Now we have square, so we can use double angle to do this. No, not this, not this, not this. Use double angle to prove this, and sine square pi xl, that has to be equals to 102 minus of cosine 2 pi x L. Let's substitute this inside. We get this. We get this. Don't forget n squared. Don't forget n squared. That's essential. That's essential. And we'll get this. I just assume that all of you just understand that I rearrange this. I factorize this and move it to here. So I'll just skip this since I'm too lazy to do this. And cosine equals to sine 2 pi sine 2 pi x over L with the boundary conditions here. And that's easy. That's the most easy and satisfying part, isn't it? We find that when x is L, it's L over 2 pi times sine 0, which is 0, right? And we minus L 2 pi sine 0, which is also 0. So basically, we just ignore this part since it's all 0, and 1 over n squared equals to L over 2. So n squared equals to 2 over L. Okay. And we can know that n equals to square root 2 over L. That's the final answer. That's the final answer. And we can say with huge proud, we can say that Cx equals to 2L sine pi xl. It looks easier than before, right? Because we normalized it. And now we can use it to evaluate something, such as the probability of this particle to be present between x1 and x2, or something such as the tunneling probability that we'll learn in probably next time, or the next time. Yeah, I'm sure. Next time we'll start with observables and operators. So this is basically the most demanding parts of quantum mechanisms. No, sorry, the most demanding part of this lecturing today about wave functions. Although this is just an introductory part for quantum mechanics, but it's better than nothing. We have been starting with quantum mechanics, and it seems pretty smoothly. It went pretty smoothly at first. 1.4, as we talked before, there is some restriction. There are some very severe restrictions over Schrödinger equation. Schrödinger equation. First is, you see, C can't be infinite, because when it is infinite, the probability of this particle to be present at this point is infinite, which is not possible at all. This is total logic over a finite region. And also, it must be single valued. It cannot have two states, two position at, no, sorry, two possibilities at one position. That's not logic, and that's impossible. And C itself must be continuous. There can't be sudden change of C. And the first derivation the first derivative of t must also be continuous. This might be pretty challenging to understand, so I'll explain point 3 and point 4. You see, we got this term in our definition about Schrödinger's Schrödinger's equation. If we have a second derivative, which means we must first get a first derivative. Oh, that's a tongue twister. And we have to get a zero derivative, which is the original function for dc over dx. If we have a second one, the first one has to be continuous. And if we have a first one, the original function must be continuous. So that's the reason, that's the explanation, that's the best explanation I can think of for point 4 and point 3. So yeah, I hope you can understand this. And all of these 4 points, they're so severe, so they lead to a horrible result, which is the quantization of energy. Yeah, that's how everything begins. That's how physics just begin. That's how quantum mechanics just develop. Because these are so severe, so the E for Schrödinger equation for this wave function, to be honest, it can't have any value. It cannot have arbitrary value, to be honest. To be more clear, arbitrary values. You cannot make it up. You cannot just fabricate a value and make the function work, make the equation work. It won't because it won't. So in other words, we'll say E is discontinuous or quantized. Yeah, this is how quantum mechanics began. So I hope this is pretty simplified explanation, and that's basically all of the introduction for wave functions and Schrödinger's equation. Yeah, and since it's the first time that I've starting a YouTube channel and to talk before so many strangers on the internet, if there is anything wrong with my denunciation, there is anything wrong with my vocabulary, grammar, microphone quality, and video quality, also handwriting or explanation, just say. I'll be happy to hear and improve this. And just little forecast. Next time we'll be talking about operators. Something like this. Okay, so that's basically for today. See you. Have a nice day and subscribe, please. Yeah, thank you. Bye.